Okay, everybody, this is meant to be sort of a consolidation of all of the equations that you're likely to encounter doing gas law problems. Because as I go through the lecture, it might be easy to sort of lose track of where those individual equations are and things of that nature. So I wanted to give you sort of a consolidated list of all of the equations that you're likely to encounter. And then as I go through the proper lecture, we'll explain really what they mean and how to use them and when they're applied. But I want to give you a consolidated list so that you can watch this video and write down a concise list with labels and all the good things so that you just have something tidy to look back on. So the first gas law that we're going to deal with in the lecture is called Boyle's law. And the equation for Boyle's law is P1 V1 equals P2 V2. And I suppose before I get too far into this, very important thing is that for all of these equations, all temperatures are in Kelvin. Kelvins. Okay, we never deal with Celsius in our equations for gases. It's always kelvins, okay? So the next one, and so, let me back up a little bit. Boyle's law is for changes in pressure and volume, okay? Charles' law is the next one. And Charles' law is V1 over T1 equals V2 over T2. So changes in volume and temperature only. Next we have Avogadro's law. And as you might expect, that one is related to moles. So we have V1 over N1 equals V2 over N2. Okay, changes in volume and moles. Okay. Then we have the combined gas law. So we're going to put several things together. P1 over V1, P1 V1 over T1, P2 V2 over T2. So changes in pressure, volume, and temperature. Okay. Next and sort of finally for this type of thing is the ideal gas law. PV equals nRT, or as some students have called it, PIVNERT. So pressure, volume, N is moles, and R is a gas constant. Gas constant, and it has a value of 0.08206 liters atmospheres over moles Kelvin. And when you're dealing with anything that has to use R, you have to make sure that these units are, everything else matches those units. Okay. Next on the list is Dalton's law of partial pressures. Dalton's law. And Dalton's law says that pressure total is the sum of the partial pressures of all the components, however many components you have. Okay? And we can relate Dalton's law to the ideal gas law by saying that pressure total volume equals moles total RT. Okay? Next, we have the concept of mole fractions. And I believe we covered this earlier in the semester, but mole fraction, we use the symbol X. So mole fraction for component A. So X of A will equal moles of A over moles total. Now, relating partial pressures to mole fractions. Okay. When we have to do that, so partial pressure of A over pressure total is equal to moles of A over moles total, which also equals the mole fraction of component A. So if I rearrange this a little bit, I can say that the partial pressure of A equals the pressure total times the mole fraction of component A, okay, or gas A. Okay, we can also use the ideal gas law to solve for molar mass. So if you don't have moles or grams, you can use the ideal gas law to solve for molar mass. So if moles equals mass over molar mass, okay, which I'm going to call M for mass, M over capital MM, then I can plug that into the ideal gas law and rearrange things a little bit, and we end up with PV equals mass RT over molar mass. Okay, so if I wanted to, I could rearrange those components and solve for the molar mass. We can also use this to solve for density of gases. Okay, so if density equals mass over volume, and if PV equals mass RT over molar mass, I can rearrange that to give me density equals mass over volume equals molar mass times pressure over RT. Okay, so now we're going to switch gears just a little bit and talk about speed of gas particles, because they're always in constant motion. But since we're dealing with energy here in relation to kinetic energy, R is no longer the same value. So here we have R related to energy. So R equals 8.314 joules per mole Kelvin. Okay, and since joules are related to kilograms, 1 joule is a kilogram times meters squared over seconds squared, that means that molar mass has to be in kilograms per mole. And that's very important to get those units correct. So the average speed of gas particles, average speed, is called the root mean squared velocity. Or speed. Velocity or speed. Okay, and it has a symbol, the Greek symbol mu, which I don't always draw very well, but it's going to look like mu root mean squared, mu RMS. And its equation, so to solve for mu RMS, equals 3RT over the molar mass under the square root. If we want to know average kinetic energy of particles, gas particles that is, so the average energy kinetic, 1/2 mass times mu RMS squared. Okay, mass and velocity, very similar to an equation that you would see in physics class. And the last equation that we have is to determine rates of effusion. Okay, and what we'll have is rate of effusion for gas A over rate of effusion for gas B is related to their mu RMS for A divided by the mu RMS for B, which equals molar mass of B over molar mass of A under the square root. And if you're confused about why that flips, it has to do with the way things rearrange and basically dividing by fractions. But that's why we end up with molar mass of B over the molar mass of A. Okay, so I hope that you have written all these down as I